Today we're going to be talking about comparing two means. If you think way back to when we had the Jamestown steel example in an earlier video, we compared the result of a single sample statistic to the population parameter. Today we're going to expand on that idea of hypothesis testing to two samples to determine if the two populations' means are different. The concept is pretty straightforward. If the means from two independent populations are the same, then the sample means will be similar. Sample means are going to differ from sample to sample, so sampling variability is expected even if the population means are identical. So we measure the difference between the sample means. If the difference between the sample means from the two populations is negligible, then we conclude that the population means do not differ. If the difference between the sample means from the two populations is substantial, then we conclude that the means differ. To draw our conclusions, we can use either confidence interval estimates of the difference in the two population means or hypothesis tests about the difference between the two population means to draw our conclusions. So when might we want to compare two means? Well, here are a few examples that we can look at. Is there a difference in the mean number of defects produced on the day and the afternoon shifts at the XYZ Hospital Products Incorporated? Do older people use fewer days of hospital care than younger people? Notice that we're comparing groups against each other instead of against the population from which the sample was drawn. Let's take a look after you have a moment or two to look at a couple of more examples. And let's take a look at the overview formula for comparing the two means. Okay, let's take a look. Most test statistics are like a signal-to-noise ratio. You have the variance explained by the model divided by the variance the model can't explain. Another way to look at it is you have the effect divided by the error. When we're comparing two means, the model we fit is the difference between the two group means. And for the noise, or the estimate of the error that we use the standard error of the differences between the two means. So our denominator is the standard error of the differences between the two means, and for the numerator we use the difference between the two group means. Let's look at a more specific formula for when we have two population means and equal standard deviations. Note here that this is somewhat of an unusual occasion because we don't normally have we don't normally know the population means and we don't normally know the population standard deviations. So this is for reference more than anything else. We make no assumptions about the shape of the populations, and the samples are from independent populations. The formula for computing the value of z is listed below. Now you'll note that on the left, if we know the population standard deviation, then we use this formula on the left. But it's also very similar to the formula that's on the right. We're just replacing the sample standard deviation for each of the groups with the population standard deviation for each of the groups when we don't know the population standard deviation. Let's take a look at an example when we know the population standard deviations. So that means which formula will we use? That's right, the one on the left. So maybe I should have said that's correct, the one on the left. Okay, let's look at the example. The UScan facility was recently installed at the Burn Road Foodtown location. The store manager would like to know if the mean checkout time using the standard checkout method is longer than using the UScan method. She gathered the following sample information. The time is measured from when the customer enters the line until their bags are in the cart. Hence, the time includes both waiting in line and checking out. Use an alpha equals 0.01 level of significance. And by now I'm sure you recall that the level of significance is the level of risk that we are willing to accept of rejecting a null hypothesis that is true. Do you remember what the first step is to the hypothesis test? That's right, it's assumed nothing is going on. One thing that we do want to remember before we leave this page, though, is one of our keywords popping out at us right here saying that we want to see if the mean checkout time using the standard checkout method is longer than using the UScan method. So it didn't say different from, it just said longer than. So what kind of test is that going to be? Is that going to be a two-tailed test or a one-tailed test? Is it directional or non-directional? So our null hypothesis is that the population mean of the standard method is less than or equal to the population mean of the UScan method. Another way that we could look at this is that the difference of 0.20 minutes in our sample between the mean checkout times is due to chance. And what's the second part of the hypothesis test? Well, still more or less part of the first step is we assume that nothing is going on, which is our null hypothesis, and then we determine what is it that we expect to get if something actually is going on, and that's our alternate hypothesis. And in this case, the mean checkout time for the standard method is longer or greater than the population mean checkout method for the UScan approach. Using all of our scholarly expertise, we've chosen an alpha significance level of 0.01. Actually, it was stated in the problem, but we can always dream. And then we do a step in step 3, we determine the appropriate test statistic, and that's a z-distribution, because we know both the population standard deviation, so we can use the z-distribution as the test statistic here. And before we leave this page, this slide, where do you expect to see the rejection region? If you remember, we can look at our inequality sign for the alternate hypothesis to give us an idea of which side we would see the rejection region on. So the greater than sign is pointing at the right, and therefore we would expect our rejection region to be on the right. Now, what's step 4? It's to create our decision rule, and in this case we're going to reject the null hypothesis if our z test statistic is greater than our z critical value, and we can find our z critical value in either our appendix A1, or we can find our z critical value using Excel using the norm.s.inverse function in Excel. I believe it was 2010 that came about, or for prior versions it's norm s inverse, and then you just put the significance level in the parenthesis and you'll get your value there. So in here, just as we were saying before, our our inequality sign of our alternate hypothesis pointed to the right, and our rejection region is to the right. So what's our next step? We're going to collect our one little sample, and then we're going to compute the value of our test statistic and make a decision. So using our z test statistic formula with the known standard deviations that we have, the population standard deviations, we calculate our z test statistic. And what did you actually get in your one little sample? Well, we got 3.13. How likely was it that we got what we got? Well, the computed value, our test statistic of 3.13, is larger than the critical value of 2.33. So, if it's very unlikely, we call baloney on the assumption that nothing is going on. So, our decision is to reject the null hypothesis. The difference of the 0.20 minutes between the mean checkout time using the standard method is too large to have occurred by chance. We conclude that the UScan method is faster. Well, what happens if we don't know the population standard deviations and we have a small sample? We can use a t-test instead of a z-test as our test statistic. And that's referred to as the independent samples t-test or a pooled t-test when we're comparing population means with unknown population standard deviations and we have a small sample in one of the groups. Most of the time we're not going to know what the population standard deviations for each of the groups are, so we substitute the sample standard deviation for the population standard deviation. And it's called the pooled test because we combine the two sample standard deviations to generate an estimate of the unknown population standard deviation. So if one or more of the samples have less than 30 observations, or fewer than 30 observations to be more correct, we use the t-distribution. The assumptions are that both populations must follow the normal distribution and the populations must have equal standard deviations, and the samples are from independent populations. In this example, in this approach, it's a little bit different in that we have to take two steps in order to calculate the value of the test statistic. And the first thing that we have to do is pool our sample standard deviations. And to do so, we use this formula on the top. Once we've pooled the sample standard deviations, we put them into the formula that is on the bottom, which can also be written as we have it here. That's just a slight change in the denominator by multiplying the pooled sample standard deviation separately for each of the 1 over n minus n sub 1 plus 1 over n sub 2. And in our pooled sample standard deviation formula, our degrees of freedom is n sub 1 plus n sub 2 minus 2. And once we've calculated the pooled sample standard deviation, we insert that into our t-test statistic formula. And although it's a busy formula, it's nothing that you can't handle. It's just simply inputting the data observations or the values for each of these symbols. And as usual, there's an example coming. In this example, Owens Lawn Care Incorporated manufactures and assembles lawnmowers that are shipped to dealers throughout the United States and Canada. Two different procedures have been proposed for mounting the engine on the frame of the lawnmower. The question is there a difference in the mean time to mount the engines on the frames of the lawnmowers? The first procedure was developed by longtime Owens employee Herb Wells, designated as Procedure 1. And the other procedure was developed by Owens Vice President of Engineering, William Atkins, designated as Procedure 2. To evaluate the two methods, they decided to conduct a time and motion study. A sample of 5 employees was used using the Wells method and 6 using the Atkins method. The result in minutes are shown on the right. So the question is there a difference in the mean mounting times? Note that here we are asking the question, is there a difference? That's one of your keywords, and it should give you an indication of how we handle the hypothesis test. Here we're going to use the 0.10 significance level, alpha significance level. So what is the first step? As usual, we're going to assume that nothing is going on. Our alternate hypothesis is, what do we expect to get if something actually is going on? Well, for our null hypothesis, we're going to assume that the population mean of the Wells method is equal to the population mean of the Atkins method. Wells method, Atkins method, and the Wells method is designated as Procedure 1. Remember that the keyword was, is there a difference? So we know that it's an equals sign that we use. It's a two-tailed test that we're going to do. So again, our null is that there is no difference between the population mean of the Wells method and the population mean of the Atkins method. And the alternate is that there is a difference between the two population means. So where do we expect to see the rejection region now based on this hypothesis and alternate hypothesis? We're going to see it on both ends of the distribution. So in step 2, we're going to determine how much risk of rejecting the null hypothesis when it's true, in other words, a type 1 error, are we willing to accept. And as usual, it's given. We're going to use a 0.10 level of significance for this problem. For step 3, we find the appropriate test statistic. Because the population standard deviations are not known and we assume them to be equal, we use the pooled t-test, and we also have a small sample, so we use the pooled t-test. Step 4, of course, is to formulate a decision rule. In this case, our decision rule is that we're going to reject the null hypothesis if the t-test statistic is greater than the t-critical value or less than the negative t-critical value. And in this case, we're told in our example that we have a 0.10 significance level. So that's a little bit different from what we've been familiar with or been using in the past. The trick here is that because our book doesn't have values for 0.1, it only has 0.01 and 0.05, you have to go to the appendix A2 to find the one-tailed value of the 0.05 level of significance with 9 degrees of freedom, and you'll find that it's 1.83. Of course, the easier method is to go into Excel and to use the, again, 2010 is what I believe it is, formula, and then the earlier editions of Microsoft Excel that you can use the t-inverse formula for. So we just put in our level of significance that we've chosen and our degrees of freedom. And remember, our degrees of freedom are n1 plus n2 minus 2. So if we go back to our formula, or our, excuse me, not our formula, but our observations, we have 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5, 6 is 11, minus 2 is 9, hence the 9 in the degrees of freedom location on the Excel formula. Now we move on to step 5. And in step 5 we collect our little sample and we calculate what we find in our one little sample. So we calculate the value of t and we make a decision. First thing we have to do, though, is we have to calculate each of the sample standard deviations, and this should bring back some good fond memories for you of when we were doing standard deviation. So we find out the standard deviation of the Wells method, which is 2.9155, and the standard deviation of the Atkins method, which is 2.0976. From there, we calculate the pooled sample variance, going back to our pooled sample variance formula. We input all of the values for the symbols that we have, and we find that our pooled sample variance is 6.2222. Next, we complete the t-test statistic and we make our decision. In our formula for the t-test statistic, we substitute in the value for our pooled sample variance, and we get 6.2222 in our formula. We input each of the separate values that we have as well, and we calculate out that we have negative 0.662 as our t-test statistic. So how likely was it that you got what you got? Well, we found it right in here in the do not reject region. So if it's very unlikely, we call baloney on the assumption that nothing is going on. Well, this appears that it's not very unlikely. So we do not call baloney. We do not reject the null hypothesis because negative 0.662 falls in the region between negative 1.833 and 1.833. It's in the do not reject the null hypothesis region. We do not conclude that there is, we conclude that there is no difference in the mean times to mount the engine on the frame using the two methods. In the bottom of the slide, I provide you the methods here for calculating it out as well, using Excel and Megastat. Now we're going to get into the really exciting part. We're going to work through a case when we assume the population standard deviations are not equal. If you don't know the standard deviations of either population, and you don't want to assume that they are equal, the best approach is to use an approximate t-distribution procedure that our book provides for us on page 367, formula 9.5. It's the safest and most practical approach, and it works well even if you are in a scenario such as those in either of our two previous examples. Our t-test statistic looks very similar to what we just used, but if you noticed, have you noticed the difference? We're not using the pooled variance here. We're using each of the individual groups' variance in the numerator of the values down in the denominator. We're also using a pretty complex, well, busy formula to calculate our degrees of freedom. And the idea is that it is reducing the number of degrees of freedom in the test which will require a larger value of the test statistic to reject the null hypothesis. The challenge with these formulas is in keeping track of all of the variables. And if you use something like Excel to manually calculate this, keeping track of the parentheses on all of these formulas. If our degrees of freedom calculation turns out to provide us a non-integer value, we just adjust the degrees of freedom downward to the nearest integer value. Let's start our example. So we have a consumer testing lab that's evaluating the absorbency of paper towels, and they're comparing a set of store brand towels to a similar group of name brand ones. For each brand, they dip a ply of the paper into a tub of fluid, allow the paper to drain back into the vat for 2 minutes, and then evaluate the amount of liquid the paper has taken up from the vat. A random sampling of 9 store brand paper towels absorbed the following amounts of liquid in milliliters, and they're listed here. An independent random sample of 12 name brand paper towels absorbed the following amount of liquid in milliliters. Using the 0.10 level of significance, and test if there is a difference in the mean amount of liquid absorbed by the two types of paper towels. Again, we have our keyword here of difference. We can look at a dot plot to see if our variances are looking equal or not. And we can take a look at this dot plot here, and we can see that our values are spread out pretty well. There's a difference in the variances, at least it appears to be the case there. And what's the first step in our analysis or our hypothesis test? Well, the first step is that we assume nothing is going on. And in this case, we're assuming that nothing is going on and that our mu1 is equal to our mu2. And our mu1 is the store brand paper towels, and mu2 is the brand name or name brand paper towels. Again, we're looking for a difference in our hypothesis test, and our level of significance, or the alpha level of significance, which is our amount of risk that we are willing to accept of rejecting the null hypothesis when in fact it is true, and that is 0.10. So we go back to our null hypothesis, and our alternate hypothesis is that mu1 is not equal to mu2. So the null hypothesis, when we assume that nothing is going on, is that the store brand towels are, the mean of the store brand towels are equal to the mean of the brand name paper towels. And then the alternate hypothesis, which is what do we expect to get if something is in fact going on, is that the store brand paper towels, the mean of the store brand paper towels is not equal to the mean of the brand name paper towels. Step 2, state the level of significance. Again, that is 0.10. That's the level of risk that we are willing to accept of rejecting the null hypothesis when in fact it is true. And then we are going to determine the appropriate test statistic, which in this case is when we'll use the unequal standard deviations independent samples t-test, or unequal variances independent samples t-test, same thing. Here we have all of the information we need in this nice compact slide. And our step 4 is state the decision rule. So we're going to reject the null hypothesis if the t-test statistic is greater than the t-critical value, the positive t-critical value, or less than the negative t-critical value. Again, because our book doesn't have the values for 0.1, you have to go to Appendix A2 to find the one-tailed value of the 0.05 level of significance with 10 degrees of freedom, and that comes out to 1.81. Or what's easier and a little more precise is you can use the Excel t.inv.2t test in Excel 2010 or above, and you can use the t inverse below 2010s. I'm not sure what the Macintosh software has, if the Macintosh Excel 2011 has the new format or not, but I would hope it does. Once we calculate our test or t critical value, we go in, we pull our one little sample of what we got, we take a look at what it is that we got with our one little sample. In other words, we calculate the value of t and we make a decision. So we use our degrees of freedom formula with all those numbers and letters in it. We fill in the appropriate values in each of those places, do all of the math that goes along with that, and we find out that our degrees of freedom are 10.88. And what is it that we're supposed to do when we have a non-integer value? We go to the next lower integer value, which in our case is 10 for degrees of freedom. Here we have our descriptive statistics that just provide the information for filling in our degrees of freedom formula and our calculations for the actual t-test statistic. We calculate out our independent samples unequal and unknown population standard deviations t-test, independent samples t-test, using this formula here, and we determine that the test statistic is negative 2.478. And with all that's going on this page, do you remember what the t critical value is? Our negative t critical value is negative 1.1812. Our t test statistic is lower than our negative t critical value, so the computed value of t is less than the lower critical value, so our decision is to reject the null hypothesis. We conclude that the mean absorption rate for the two towels is not the same. Something is going on. Wasn't that exciting? Well, so far we've been talking about different groups and comparing their means, but these groups are not related to each other in any way. Next, we're going to look at a situation when the samples are related to each other in some way. That situation is referred to as the dependent samples t-test. So let's take a look at that. The dependent samples t-test is also sometimes called the paired samples t-test or the matched pairs t-test, and it involves groups of samples that are paired or they're related in some way, in some form. So if you're looking to buy a car, you would look at the same car at 2 or more different dealerships and compare the prices. That's one example of a paired samples or dependent samples t-test scenario. And another example that's a little more healthcare related is if you wish to measure the effectiveness of a new diet, you'd weigh the dieters at the start and the finish of the program. So how do we calculate the t-test statistic for a dependent samples t-test? We've already got all these other formulas running around in our heads. Let's add one more. But you'll notice this one isn't quite as complex as all of the rest of them. Or is it? So we use the following t-test when the samples are dependent. T is equal to d bar minus the mu sub d divided by the standard deviation of d divided by the square root of n. And this is the standard error of the differences. I think I said standard deviation, so just to clarify, this is the standard error of the differences. And we can look at this all in the where d bar is the mean of the sample differences, s sub d is the standard error of the differences, n is the number of pairs, mu sub d is the difference we would expect to find between our population means, and usually that mu sub d is equal to 0, and the degrees of freedom is the number of pairs minus 1, which equals n minus 1. And of course, we have an example. Nickel Savings and Loan wishes to compare the two companies it uses to appraise the value of residential homes. Nickel Savings selected a sample of 10 residential properties and scheduled both firms for an appraisal. The results, reported in thousands of dollars, are shown on the table at the right. At the 0.05 level of significance, can we conclude there is a difference in the mean appraised values of the home? And let me go ahead and change that to thousands. Again, what is step 1 of the hypothesis test? Assume that nothing is going on. Remember, our keyword here is a difference. So the null hypothesis is that the mu sub d, which if you remember, mu sub d is the difference we would expect to find between our two population means, is equal to 0. And the alternate hypothesis, which is what we expect to find, or if something is going on, what do we expect to find? And that is the mu sub d is not equal to 0. The level of risk that we're willing to accept of rejecting the null hypothesis when in fact it is true is 0.05, and that's given to us in the problem. And then we're going to find the appropriate test statistic, and we're going to use the dependent samples t-test that we found in this slide here, slide 23. Another way to look at the null hypothesis is in words, and that is to say that the population mean of the sample differences is equal to 0. And this is a little different from what we're used to seeing. The question is whether the sample differences in the appraised values could have come from a population with a mean of 0. If the population of the differences is 0, we would conclude that there is no statistically significant difference in the appraised values. And then the alternate, of course, is that the mean of the sample differences is not equal to 0. And where do we expect to see the rejection region? Again, it's a two-sampled or two-tailed t-test, so we should expect it on either end of the distribution. Here we have our decision rule. We're going to reject the null hypothesis if the t-test statistic is greater than the t-critical value, or the t-test statistic is less than the negative t-critical value. And we can find that in the back of our book in Appendix A2. And because it's two-tailed test at the 0.05 level of significance, we do have that in our book. And we use 9 degrees of freedom, and it comes to 2.262. Of course, you can also use Excel, and you can use either of these two functions to find that out. So step 5, we're going to go ahead and collect our one little sample to find out what we got. We're going to compute the value of t to make a decision. We're going to see with our sample how likely was it that we got what we got. And if it was really unlikely, we're going to call baloney on the assumption that nothing is going on. So what did you actually get in our one little t-test or our one little sample? Well, we got a t-test statistic using our t-test formula of 3.305. How likely was it that we got what we got? It was unlikely. The t-test 3.305 is greater than the t-critical value of 2.262. So we make the decision. If the results are very unlikely, we'll call baloney on the assumption that nothing is going on. In this case, it is very unlikely. We reject the null hypothesis because 3.305 falls in the rejection region above 2.262, our t-critical value on the positive side. So we calculated out the difference, which was just simply subtracting Bowyer from Shadek to find 7 in this one, and we did that for each of our samples or sample homes that we had. We summed all of that up to get our average, our D bar, and so we had 46 divided by 10 homes that we had, and we got 4.60. Then we took the D, or the difference, minus the D bar value to get our D minus D bar values for each of the 10 homes. And of course, when you calculate all of those up, they should equal to 0. And then once we have that, we square that value for each of our homes, and we sum all of that up. This should remind you of how we're calculating out standard deviation, but here it's called the standard error of the differences. So we run through the calculation, and we get 4.402 as the standard error of the differences. Now we have the information to put in our calculation. So we put d bar is 4.6. The minus mu sub d is that we're assuming, if you remember in our hypothesis, that mu sub d is equal to 0. So we have 4.6 minus 0 equals 4.6. And then we put our standard error of the differences divided by our square root of our n in the denominator, 4.402 divided by the square root of 10. All of that together equals 3.305. And tell the truth now, wasn't this more exciting than anything else you could have been doing besides watching a video about how to compare means? Well, that's all we have for you today. See you on the next video.